So my goal is to give you a smattering of different algorithms, just so that you can, because you know what happens is in a lot of cases, the standard projection schemes are just really bad ideas. One setting why when it might be a bad idea is that it requires you to project onto the set. If that set is a very nasty set comprising of lots of nonlinear but convex constraints, it's a very slow algorithm. So you'll see settings which differ. But most of the avenues I have here have some projection component. Here, Arno, she sent you a copy of the slides. Okay, so here I'm going to talk about Tikhonov trajectories. The reason why I wanted to talk about Tikhonov is because there's been a discussion about regularization. And I think it's important for us to understand what happens when you have regularization, okay? Particularly in monotone cases, okay? So, and that's when this wonderful research on Tikhonov regularization assumes relevance. So this was actually initiated by work by Arsenin and Tikhonov. And the idea is the following. If I give you just a continuous mapping, right? If I give you a continuous mapping, then the sequence x epsilon is immediately bounded. Okay, and so what is x epsilon? So if I give you a map f plus epsilon I, so so this is a monotone mapping. F plus epsilon I is a regularized map. What is the intuition for that? The intuition is the following. If each player is solving a problem theta 1x, if I add an epsilon x1 squared, this is equivalent to getting a solution to x f epsilon x, or I can also write epsilon identity map. Okay. Why is that? When I differentiate this, I just get x1. If I differentiate this, I get xn, and so on. Now, why is this map? So the first question I have is, if f is monotone, can you prove that f plus epsilon I is strongly monotone? Right? So sometimes what happens is you say, oh, I've got a map, I think it's monotone, but I don't know the monotonicity constant if it's strongly monotone. If I just regularize it, I immediately get strong monotonicity. And if you're interested in approximate solutions, this is not a bad idea. Okay? So for instance, in this case, if you want to check for strong monotonicity, it's not difficult. You say epsilon x minus f of y minus epsilon y. So I'm trying to prove that the map is strongly monotone. So how do I prove that? I prove it as f bar x minus f bar y transpose x minus y, which is the same as f of x minus f of y transpose x minus y plus epsilon times x minus y transpose x minus y, which is the same as, now what is this? If a map is monotone, what do we know about f of x minus f of y transpose x minus y? It's always greater than or equal to 0, right? So this is greater than or equal to, and what is this? Norm x minus y squared. So you're left with x minus y squared times epsilon. So the monotonicity constant is epsilon. Okay, it's not too difficult to do this. So now, if I try and get a solution to the strongly monotone map, then what we have is epsilon x. So let's write this out. So why does this hold? This holds from the property that x epsilon is a solution of this. If it's a solution of this, x minus x epsilon times this has to be non-negative, just by definition, right? If I tell you x epsilon is a solution of x f plus epsilon I, then what we know is x minus x epsilon transpose f of x plus epsilon x has to be greater than 0 for all this is x epsilon for all x in x. Okay. Now, if you look at this relationship, let x bar be fixed. And what you can do is, just write this out, f of x bar, so if you look at this, f of x bar transpose x bar minus x epsilon. Okay, let me just write this out. Okay. So the preceding relationship, one second, I want to see what I do here. X bar. One second, what have I done here? Is greater than. Okay, I think. Oops. One second. What did I do? I'm suddenly forgetting how I got that. Okay, let me write it out just so that we know. So, if I have some x bar, so I have f of x epsilon, sorry, second. Transpose, okay. So I have f of x, so if I, okay, I think I know what I've got. So we know this holds for some x bar. And I also have that f of x epsilon minus f of x bar transpose x epsilon minus x bar, or let me go the other way. F of x epsilon minus f of x bar minus f of x epsilon is greater than, plus this is plus epsilon. So what I had from the regularized map, epsilon x is greater than 0. So what I'm left with is, if I add these two, I'm left with f of x bar transpose x bar minus x epsilon is greater than, so I've added this, I've got that. I take this to the other side, minus x epsilon transpose x bar minus x epsilon. What do I have now? Okay. Right. Did I screw up something? One second. Oh, I think I've subtracted the wrong way. One second. What did I do? What did I do when I drew this? One second. Sometimes what happens if you take the wrong side, it doesn't work. This, and you're adding. Yeah, I'm trying to figure out if I made a mistake in this. Hang on. No, okay, let me just start again. Let me just prove it directly. Okay. So you start from, since x epsilon lies in the solution set of x f plus epsilon I, what we have is x bar minus x epsilon transpose f of x epsilon plus epsilon x epsilon is greater than 0. Okay. And now based on x bar is fixed, so you have f of x epsilon transpose x bar minus x epsilon is greater than x epsilon minus x bar transpose epsilon times x epsilon. Okay, right? That's right. So then what you're left with is epsilon times x epsilon minus x bar. Suppose x epsilon minus x bar plus epsilon times x bar transpose x epsilon minus x bar. So this is equal to epsilon times x epsilon minus x bar the whole squared. So epsilon times x bar transpose x epsilon minus x bar. I think there's an epsilon missing there. Must be. There's no other way for this to happen. Okay. Now by monotonicity of this, what we have is we know that f of x epsilon transpose x bar minus x epsilon. So what you know is this. So if you look at this, is less than f of x bar transpose x bar minus x epsilon. Why is that? From monotonicity. So from the left side, I can introduce this, and then I have this plus epsilon. So now what you have is epsilon x epsilon minus x the whole squared. And now if you take this to the right side, you have x bar times x epsilon minus x plus f of x bar times x bar minus x epsilon. So x, okay. Okay. So then what you're left with is, okay, right. So missing, I've got an extra epsilon showing up somewhere which I'm not sure about. Anyway, for the time being, so what you do is if you take this to the left side, what you're left with is the following. What you're left with is epsilon times x bar minus x epsilon squared is less than f of x bar transpose x bar minus x epsilon plus, I'll check the constant. There's a constant that I'm missing, and I'm wondering whether there's something I've seen, whether there's something from the previous one that I've missed. Trying to see where I've. Anyway, okay. So then I have. So this can be bounded by norm f of x bar, norm x bar minus x epsilon, plus norm of x bar, x epsilon minus x bar. Where do I get that from? This is just from the property that u transpose v is less than norm u times norm v. This is just the Cauchy-Schwarz inequality, right? It's Cauchy-Schwarz. So then this cancels with this and this, which means that x bar minus x epsilon is less than plus okay. Showing that x epsilon is bounded. Okay. Okay. So this is for a fixed bound, okay, for epsilon greater than epsilon bar, right? So this epsilon is greater than epsilon bar, so that this is less than now, when epsilon goes to 0, the sequence may not converge. So let's give you an example of that. Let's take the simple LCP where m is 0, 1, 0, 0, okay, and q is minus 1. Now, if you look at the regularized LCP, this is m plus epsilon I, and it has a unique solution 1 upon epsilon comma 0. Now, you can see that the distance from x 1 upon epsilon to the solution of qm is 1 for all epsilon, right? But you can see that what happens is that epsilon goes to 0, this is blowing up, right? So one thing that you have to remember is that regularizing always does not help. Sometimes if you regularize, the solution itself gets affected by the regularization parameter, and that effect shows up in the reciprocal. So as epsilon goes to 0, this thing blows up. So you have to be a little careful about how you do this. In this case particularly, the map wasn't monotone to begin with. So when it's not monotone and you put an epsilon here and here, you can have strange things happening. So you have to be a little careful about how you regularize these problems and when to regularize them.
Sorry,
Yeah.
I have a question. So when we started out, we added epsilon to our a term of epsilon to our objective function for each of the.
I only did that to show you that the map gets regularized, but in general the thing is that you just directly add it to the map. But that was just to motivate it from where it shows up in a game-theoretic setting.
Okay, but then shouldn't epsilon tending to 0 make it more closer to the original problem?
Yeah, it does. And so in some sense, but remember, just because you make it closer to the original problem, the sequence that you're generating is with a different problem. And now that sequence might be basically going away, because the problem is that epsilon is showing up in the map. And so the x epsilon is affected in some way, right? But your intuition is correct, that we should get something, and that's what happens if the map is nice. If the map is really poorly behaved to begin with, this modification might worsen it. So for instance, if f is a continuous monotone map on K, then this limit x epsilon exists. And what I mean by that, it's finite. In the previous case, when you saw the limit, it was plus infinity, right? It was 0, 1 upon epsilon, so it was going to plus infinity. Now, if the limit exists, then the sequence is bounded. This holds in general. Otherwise, if the sequence wasn't, because you know that when you have that the limit exists, you can put a ball around that, and all but finitely many of those iterates are going to be in that ball. Okay, so this is from standard analysis. The second question is, how do you show that the set is non-empty? So one of the reasons why having bounded sequences is so important is that when you have a sequence that is bounded, what happens is that you immediately know that you can pull out a convergent subsequence from it. Okay, so if the sequence is bounded, this sequence is bounded. And how do you know the sequence is bounded? Well, you know the sequence is bounded because the limit exists. So you know that there's a convergent subsequence. This is just from analysis, right? So if you have a sequence that is bounded, there's a convergent subsequence. Since the subsequence is convergent, let x bar be the limit point of that subsequence. That subsequence is denoted by x epsilon k. Okay. Now, since along that subsequence you have that the solution property holds for the VI, what you have is this requirement. F of x epsilon k plus epsilon k times x of epsilon k, which is the value of the regularized map, transpose x minus x epsilon k. What is that? That's just the optimality relationship for the VI, the regularized VI. Now take limits. If you take limits, what happens? This goes to x bar, this goes to x bar, this goes to x bar. And what happens to this? This goes to 0. So you're left with f of x bar transpose x minus x bar. But we know that on the right side, this was always greater than or equal to 0, right? Because this whole thing was always non-negative from here, right? Which means that f of x bar transpose x minus x bar is non-negative, which means that x bar lies in the solution of the map, of the problem. But let's be careful of what I've said. I've said the sequence is bounded. If you magically could compute x epsilon for every k, and if you just took that and you ran epsilon to 0, that sequence is not convergent. We don't know if it's convergent. But what we know is there is a convergent subsequence from that, and that subsequence converges to a solution of this problem. Okay? And so, for instance, in the case of monotone problems, you know that the subsequence is convergent. It converges to a point in the set, which means the set has to be non-empty, which means the original problem has to have a solution. So you can use Tikhonov trajectories to provide an existence result, and a constructive existence result from an algorithmic standpoint. Because the sequence converges, it has to converge to a limit point. That limit point has to satisfy the optimality criterion, which means that the solution set has to be non-empty. Okay, does everybody understand the intuition of this? Okay. Now, we still need to do the last part. So remember what we said, these are all equivalent. So to show all three are equivalent, you need to show A implies B, B implies A, B implies C, C implies B, and so on. So an easy way to do it is A implies B, B implies C, and C implies A. So we did A implies B, we just did B implies C. Let's do C implies A. So to show C implies A, we need to show that if the solution set is non-empty, we need to show that the sequence, the limit exists. Okay. So now since this x epsilon lies in the solution of k f epsilon, we know that that holds for any iterate. So remember what we know. We know that the solution set is empty. Right? And what we're trying to prove is that the limit exists of this x epsilon sequence. So for any x star and any epsilon, we know that the optimality with respect to x star is satisfied by this. So let me just write this down. Okay. So we know that C implies A. So we're starting with the solution set of KF is not equal to the empty set. So which means that we're going to start by saying And for any epsilon, we have a solution to the Tikhonov iterate, which is x minus x epsilon transpose f of x epsilon. Okay. For any x star, we have x minus x star specifically we have x epsilon minus x star transpose f of x star is greater than. So this is from the fact that x star is a solution. This is from the fact that x epsilon is a solution of vi k f epsilon. By monotonicity, what we know is x epsilon minus x star transpose f of x epsilon minus f of x star is greater than 0, which implies that x epsilon minus x star transpose f of x epsilon is greater than x epsilon minus x star. And we know this is greater than equal to 0. So we have that this is greater than equal to 0. So then, now what I do is I add this and this. Okay. So I add this and this for x star, 1 and 2. And if I do that, what I'm left with is epsilon x epsilon transpose x star minus x epsilon is greater than equal to 0, which implies that epsilon norm x squared is greater than epsilon times epsilon times x epsilon transpose x star is greater than epsilon times, right? This cancels. By Cauchy-Schwarz, this is less than x epsilon x star. If I cancel this, this knows that x epsilon is less than x star for any epsilon. And x star in solution F. Okay, so the first thing is I've shown that this is bounded. If I just use bounded, now consider the case when the norm of x epsilon is not 0. Right? So let x star be the smallest norm solution. So we know that any limit point x bar has to satisfy x bar less than x epsilon. Why is that? Because I've told you x epsilon is less than x star. So any limit point has to satisfy this. Why is that? If I took limits on both sides, what happens? And I've told you this is less than x star. So then any limit point of this has to satisfy that, right? So now, in view of any limit point has to satisfy this. This and the fact that x star is the smallest norm solution implies that x bar is equal to x star. Okay. Now consider the case when x epsilon is equal to 0. Okay. So if x epsilon is equal to 0, then what you need to do is basically substitute 0 instead of x epsilon. And what you find is the smallest norm solution is x star equals 0. And we have that x epsilon will coincide with the small norm. Okay. So by eliminating those, of course, we can focus on values where with x epsilon not 0, for which the analysis of the preceding case holds. Okay. So what I want you to realize is that the Tikhonov trajectory, and this is important, converges. So when it converges, you have the solution, it converges to the least norm solution. It doesn't just converge to any solution, but to the least norm solution. So you can see this, because x epsilon is less than x star for any x star. So if the one thing that you want to take away from this discussion is the Tikhonov trajectory is convergent for monotone maps, and that it converges not to an arbitrary solution, but the least norm solution. Now you might say, why do you care? Lots of settings where the least norm solution is relevant. So for instance, if you're looking at machine learning problems where you're interested in sparse solutions, then the least norm solution is of relevance there. Lots of settings where this kind of regularization is useful. You don't just want an arbitrary solution. Whenever you solve an optimization problem where you've got multiple solutions, the type of solution you get sometimes is irrelevant to you. But there are instances when you'd like a particular type of solution. One setting is machine learning, particularly compressed sensing. You'd like sparse solutions, and this is one avenue for recovering sparse solutions. Now, the idea can be used, this can be extended to this notion of using a G trajectory, which is basically instead of using just adding epsilon I, you can add any other monotone map G and get a solution to this problem. Okay? Again, similar results appear, but I'm not going to prove them here. Now, if f is continuous and the solution set is non-empty and bounded, then the sequence generated by the Tikhonov regularization method is bounded, and each of its limit points lies in the solution set. Okay? Now, here's an avenue. Now, one of the problems is as epsilon becomes closer and closer to 0, the solution of the monotone problem gets closer and closer to just monotone. So that problem becomes harder to resolve. What would be nice, and when I say harder to resolve, it's because if you're looking for solving strongly monotone problems, those are easy to solve when epsilon is large. When epsilon is small, think what happens. I mean, look, if you're trying to solve them, suppose you're trying to use this method, the projection method. What happens in the projection method what happens in this method when eta becomes small? What happens? So if eta is 10 raised to minus 4 and L is 10 raised to 4, then the step length is 10 raised to minus 4 divided by 10 raised to 8, which is 10 raised to minus 12. It's a very small step length. So as eta becomes very small, methods which are supposed to work well, despite the fact that they give you linear convergence, they use a contraction factor which is ridiculously small, something of the order of 10 raised to 1 minus 10 raised to minus 12. Right? So the point is that epsilon is small, it doesn't matter that it's strongly monotone, it's just very difficult to solve using these methods. So you'd like to have a situation where the epsilon doesn't go to 0. Okay? So the question is, how do you do that? Well, that was it was first kind of discovered by Rockefeller and also people before him using this idea of proximal point methods. Okay, so it's based on a Tikhonov regularization idea, but instead of using, something has happened here. Let me just. One second. One second, I'm just going to recompile that. I think there's some space issue that, yeah. Oh no, this is the wrong one. Yeah, this is better. Okay. So what proximal point methods do is they use a different perturbation. They use this. Let me just show you what they do. They use the previous iterate as a basis to analyze the problem or to compute a solution. So if I told you, so let's take a simple problem. If I told you I have a problem like this where f is convex and I want to solve another optimization problem, but I want to make sure I'm close to my previous iterate. Now what can you tell me about, if f is convex, what is the convexity property of this function? This is called a proximal term, x minus xk squared. So you want a solution such that the solution is close to xk. So what do you think the convex is this problem, is the function f, is it convex or is there something stronger you can say? It's strongly convex. So if f is twice continuously differentiable, what you know is this is mu times I. And what you notice is regardless of what xk is, the convexity constant stays the same. Now from a vi standpoint, what that means is, suppose I want to solve this vi, f plus, what do I use, mu? Let's say I'll use mu x minus xk. So this is the original mapping plus some modification, and it just stays away from, you just need to be close to this. So that's the same as x f plus mu times the identity minus some constant. Okay, so I want to solve this problem. Now what is the monotonicity constant of this problem? So if the original problem is merely monotone, the new problem is strongly monotone with a convexity constant mu. And that's in your hands. And it doesn't go to 0. Right? It doesn't go to 0. So that problem has better properties. You could choose mu as being much larger if you so choose to do so. Right? So now proximal point method, and that's what this is. The c is like the mu that I have there. It's just the reciprocal of that. X is the centering term for the proximal parameter. So it's x plus x minus this x which is fixed. Okay? So you can see that this is strongly monotone, not difficult to see, with a particular constant, 1 in this case, because I've used I minus x plus cf. Okay? So c is like 1 upon mu in this case. Okay? So here's the algorithm. In the previous case, what do? We solved a sequence of problems of the form f plus epsilon k times x, where the monotonicity constant is going to 0. Here you solve a sequence of problems of this form, f plus I minus xk. So as xk gets closer and closer to x star, assuming it converges, what's going to happen is that you're going to find that this effect is getting more and more mitigated. Okay? So let wk be this solution of phi of ck, and I'll tell you what that is. And then you average between xk and wk, and then you update. Okay? So I want to just show you. So I want to just talk about the algorithm. I'm not going to prove it today. It's quite late. I'd rather just spend time on the code for the. So what happens is that you have to remember one thing in this scheme. In the Tikhonov scheme, we directly use a solution of this. In this scheme, look what happens. So what you're doing is that the new iterate is the old iterate weighted by 1 minus rho k plus rho k times a solution to some new iterate, which I'll define. And this can be written as xk plus rho k times wk minus xk. So a way to visualize this is xk. This is the direction from xk to wk. So I move along this direction by rho k, and I add that to xk. So suppose I'm at xk, I move along this direction by an amount rho k, and the direction is wk minus xk. And I move to this new iterate. And the amount that I move by at every point gets updated. So row k plus 1 gets updated, ck plus 1, which is the weight on this, can also get updated, but in general I can keep that constant. But remember, ck doesn't go to 0, it stays within some boundary. It's always greater than some c bar. Okay, so the monotonicity constants do not plummet to 0, right, like they did in the previous case. So now in this case, what you find is that the sequence generated by this converges to a point in the solution set. Okay. So tomorrow when we start off, we'll prove this result, and before moving to more general problems in the stochastic region. Okay. So I want to stop here, and maybe we can spend some time on the coding. Okay. So what I'd like to do is that yesterday I felt like I didn't do a good enough job of making sure everybody was on the same page. So I'm going to go around, make sure that everyone has their code. And for those of you who are sharing, we can make sure you can see that. And for those of you who've been able to get the code done, we'll see how to move forward. Okay. And I'm going to start, once I get people set up, I want to start telling you what the next steps are. So my final goal is I'm hoping that we can code some simple algorithms on the network. Okay. That's what I'd like. So let's see if we can get that to work.